Your skates don't melt the ice. A liquid layer, just a few nanometers thick, was already there before you stepped on. For over a century, we were taught the opposite, that a skater's weight squeezes the ice hard enough to melt it and glides across that meltwater. That explanation is a myth, and the real one wasn't nailed down until physicists could look at the ice surface molecule by molecule. Let's cut it open. Here's the pressure melting story you probably learned in school. A skate blade concentrates a skater's full weight onto a sliver of steel barely a millimeter wide. That squeezes the ice with enormous pressure, and pressure lowers ice's melting point. So, the story goes, the ice beneath the blade briefly turns to water, and the skater glides on that thin puddle. It's a tidy explanation. It's also nowhere near strong enough. Run the numbers. Even under a skater's full weight, the pressure only lowers ice's melting point by a fraction of 1 degree Celsius. Nowhere near enough to explain skating at -20. And pressure melting can't explain why a hockey puck, a shoe, or your own boots slide on ice too, with none of that concentrated blade pressure at all. Something else is going on. The real answer. The very top layer of ice is always slightly liquid, even in a deep freeze, with no pressure required. Water molecules on the surface have no ice above them to lock them into the crystal, so they wobble loose in a thin, slippery film only a few nanometers thick. Physicists call it the quasi-liquid layer, and it was first guessed at by Michael Faraday in 1850. It just took modern instruments to actually see it. Skating does add one more ingredient: friction. As a blade or a boot slides across that already slick film, rubbing generates a little extra heat, which thickens the liquid layer right under your foot and makes the glide even smoother. So friction isn't the main cause of slipperiness. It's a booster on top of a surface that was already halfway to wet. This explains something pressure melting never could: why ice gets less slippery the colder it gets. Close to freezing, that quasi-liquid layer is thick and easy to slide on. Drop the temperature toward -30, and the film shrinks down to almost nothing, so the ice starts to grip like sandpaper. Ask anyone who's walked on Antarctic ice in deep winter. It barely slides at all. That's why skating rinks are kept just a couple of degrees below freezing, not colder. It's the sweet spot for the thickest, slickest film. It's also why an ice cube fresh from the freezer feels grabbier than one that's been sitting on the counter starting to sweat. Same ice, different amount of that molecular film. So ice isn't slippery because you melt it. It's slippery because its surface is never quite solid to begin with, a permanent, nanometers-thin sheet of liquid sitting right on top, waiting for you to step on it. If that changes how you think about the next patch of ice you walk across, that's the whole point of this channel. Subscribe at Cutaway 360. We keep cutting things open.